Welcome to lesson number 5. Previously we explored the concept of feed-forward, and we delved into the mathematics of how an input is processed throughout the depth of a neural network to eventually produce some kind of output. We then saw an example of a model which incorrectly classifies our data, which is why we're going to shift our discussion over to backpropagation. We need some kind of algorithm to train our model to better classify this training data, and really, it's no different than how we previously did it for the single perceptron. We've already labeled this training data as either 0 or 1. Everything red denoting a label of 0, and everything blue a label of 1. What we can do now is take our training points with random x1 and x2 coordinates and pass them all into our neural network in a feed-forward process, which ultimately is going to produce an output. As you can see, some of the predictions made by the model are correct, but a lot of the predictions on the red points are incorrect, which makes sense since the model clearly misclassifies a lot of them. Since we've already labeled all of this data, the output predicted by the neural network is compared to the actual output which we've already labeled. We're comparing the difference between the two to obtain some kind of error. The more our model misclassifies the points, the larger the error. And just like how we implemented gradient descent on a single perceptron, this error is then backpropagated to constantly update the weights of our neural network, thereby updating all the models and gradually decreasing the error, iteratively passing batches of data throughout the neural network and updating the weight and the direction with the smallest error. This is gradient descent all over again, except this time, instead of updating the weights in a single perceptron for one linear model, we're updating the weights of all the models throughout the entire neural network. Recall that even though with gradient descent we're updating the weights and moving in the direction with the smallest error, we need to do it in small steps, especially when there's a lot of data. At the moment, the lines are adjusting themselves at a very specific learning rate, which simply determines the amount by which the weights are changing at every iteration. Eventually, our neural network determines that these are the optimal weights, which will ultimately come up with a model that best classifies our data and minimizes the error. Therefore, at its root, to train a neural network, we need to minimize the error function. What is that error function? Well, remember this little thing we called cross-entropy, which was simply the average of the ln of the prediction of the blue points plus the ln of the prediction of the red points, where high cross-entropies indicate a lot of error, a bad model, whereas a low cross-entropy indicates a low error, a good model. If you don't remember what cross-entropy is, I would highly recommend revisiting the last section, but essentially, even with a deep neural network, we're still applying that same equation. We're still using that same error function. But, as you saw in the last video, to compute the prediction and the output with a deep neural network, it occurs in a feed-forward process, where the inputs traverse the entire depth of the neural network in a series of sigmoid activation functions, where eventually an output is obtained. Whereas with the single perceptron-based network, it didn't have to go through any hidden layers. But regardless of how the prediction is obtained, we're still taking the probability of all the blue points being in the positive and all the red points being in the negative region, adding them all up to obtain the total error. To recap, first we conduct a feed-forward operation on previously labeled data to obtain their prediction, where we can then apply the error function on all the probabilities to determine the total error. This error is then backpropagated in a reverse feed-forward operation to update the weights of all of our models throughout the neural network, and we keep doing that iteratively, over and over at some learning rate until we obtain a good model. How exactly does backpropagation work for a deep neural network? Let's talk about that in the next lesson.